This is lab number 6 by group 4. In this experiment, we're exploring the behavior of capacitors and how they store and release electrical energy over time in what's known as an RC circuit. This simple setup includes a resistor, a capacitor, and a power source. Capacitors are devices designed to hold an electric charge for a short period of time, and their ability to store and release energy is what made modern electronics possible. Without capacitors, we wouldn't have devices like cell phones, computers, or even car radios working as smoothly as they do. In an RC circuit, when we apply voltage, the capacitor begins to charge, quickly at first, and then it gradually slows down as it approaches its maximum charge. So when the circuit is disconnected, it discharges in the same gradual way. And the key measurement that describes this process is called the time constant, which is represented by the Greek letter tau, which equals the resistance multiplied by the capacitance. This value represents how long it takes for the capacitor to reach about 63% of its full charge. This concept might sound a little weird, but it's used in many real-world technologies. For example, capacitors are used in camera flashes. They charge up and release a burst of energy all at once when you take a picture. And they're also used in heart pacemakers where a capacitor discharges periodically to send a precise electrical pulse that keeps the patient's heart beating as it should. So in this lab, we're not just looking at how capacitors behave, we're quantifying it. So by recording the capacitor's voltage over time, we can see exactly how charging and discharging curves behaves and calculate the tau experimentally. Then we'll compare to the theoretical value to understand where the differences of percent errors come from. And through this process, we'll get a better sense of how the energy is stored, resistance, and time all interact with each other and in an electrical system. For this lab, we use capstone signal generator, a voltage current sensor, a 10 ohm resistor, and a 330 microfarad capacitor, all connected on the circuit tablet. The signal generator produced a 1 Hz square wave at 5 volts, which allowed the capacitor to charge and discharge repeatedly. And we adjusted the settings to record for 3 seconds and then increased the rate to 500 Hz so that the software could capture the faster voltage changes accurately. The voltage current sensor was placed across the capacitor to measure how voltage changed over time, and this data helped us to see the changing and discharging curves and calculate the time constant, or tau. And the 10 ohm resistor controlled how quickly the capacitor charged, while the 330 microfarad capacitor stored the electrical energy in its plates. So together they formed the RC circuit that we saw. And later we added a second capacitor and tested both series and parallel connections to compare their equivalent capacitances and percentage errors. So overall, the signal generator provided the power, the resistor and capacitor determined the circuit's behavior, and the sensor, along with capstone, allowed us to record and see our results accurately.
For our procedures, the equipment setup included a signal generator setup, a sample rate adjustment, and circuit connections. For the signal generator setup, the set waveform to positive square wave, and we had to set the frequency to 1 Hz and the amplitude to 5 volts. In order to check the data, we had to check the auto box, then open the stop condition panel, choose a time base, set the record time to 3 seconds, then press OK to automatically stop the experiment. For the sample rate adjustment, we had to go to the rate zone at the bottom of the page and set the voltage current sensor rate at 500 Hz for high-speed data collection. For the circuit connections, to build a series circuit we included the signal generator, a 10 resistor, a 330 capacitor, and on the circuit tablet, the bypass the coil by connecting a single jumper wire across its terminals. For step 1, we had to place a voltage sensor across the capacitor, Then click record and allow Capstone to automatically stop the experiment. We then zoomed in on full cycle showing charging and discharging of the capacitor. Then use the add coordinates tool to find the time when voltage and the time of voltage at 63% of total voltage. We then subtracted these times to determine the experimental time constant. We then used the time constant to calculate the capacitance. And then we compared our calculated capacitance to the value printed on the capacitor. For step 2, we had to connect both capacitors in parallel, then add the resistor in series with the parallel capacitors, then place the voltage sensor across the junction of the capacitors. The theoretical equivalent capacitance gave us the sum of both capacitors, then measured data to determine the experimental capacitance. Lastly, we did calculate the percent error between experimental and theoretical values. For step 3, as a group, after reviewing all the data, we compared all the time constants. We were able to compute the total resistance and its percent error.
The formulas that were utilized for the quantification of capacitance and change in voltage capitalizes on the process that occur in a simple RC circuit. So here on the right, you could see the formulas that were used to calculate the time constant in an RC circuit and the percent error for both our experimental and theoretical capacitances. In this experiment, we systematically monitored and quantified the amount of voltage that was charged to acquire the elapsed time. And doing so, we were then able to acquire experimental and theoretical capacitance of the capacitor. And we found those values by taking into account the equation T equals RC and rearranging it into C equals TR in order to find the experimental capacitance. With the constants of resistance of 33 ohms, we then compared the experimental to our theoretical, which is 100 farads, and it revealed a somewhat normal percent error for our first table. And then for our next table, we connected 2 capacitors in parallel and 1 in series, and the previous steps were taken to acquire the same values. And here, the manipulation is the addition of a second capacitor, and how the alternation of position may alter the voltage and capacitance of both. And the last percent error shown in figure D shows that we may have miscalculated or made a mistake with choosing the wrong cycle, which may explain why the percentage is so high, but more of our thoughts will be elaborated on in our conclusion.
For our conclusion, we noticed that most of our percent error came from small things like timing delays when we marked voltage points, the sensitivity of the voltage sensor, and a bit of resistance in the wires or connections. These might seem minor, but they add up, especially in short time measurements like hours. If we wanted better results, we could improve our setup by double checking the calibration, using tighter connections, and maybe increasing the sampling rate so Capstone collects more data points per second. Our time constants were generally similar and matched what the RC formula predicted. When we added a second capacitor in parallel, the total capacitance went up, which made the circuit charge more slowly, just like theory says. The percent error for the single capacitor was higher, while the parallel setup had a much lower error, and that difference makes sense because adding capacitors in parallel decreases total resistance and makes the reading smoother. When we calculated total resistance using the capacitance values, it was close to what we expected, with a small percent error caused mostly by internal resistance from the components and wires. Overall, our results supported the TRC relationship, even though we had some experimental error, the patterns we saw lined up with the theory and showed how real circuits behave, especially how capacitance and resistance work together to control charge and discharge rates. And that is the end of our presentation. Thank you for sticking around to the end. If you have any questions, you can please contact us at jalopez74@miners.utip.edu. Thank you.